Hello and welcome. In this video, we're going to take a look at everybody's favorite kind of problem, word problems. Just kidding. What we're really looking at here is how to take a problem where it's an applied visual problem and transform that into a mathematical problem. And that's actually usually the toughest part. Once you've got an equation, we've already kind of looked at some typical types of equations and know how to solve those. It's usually a problem about translating all of these words into mathematical concepts. So in this video, we're mostly going to look at geometric kind of problems involving length and area or angles, that kind of thing. And then in another video, we can take a look at some of the more obscure problems that may cause you even more headaches. So let's start off with a problem that's just involving area and length. Here we've got a problem where we know that a rectangular pool is twice as long as it is wide, and if the area of the pool is 50 square feet, then what are its dimensions? Well, the first step I'll recommend is to try to identify what variable is in the question. In other words, what is actually being asked here? And then we can give that quantity some sort of symbolic letter, for instance, in this case. So here we can see that we know things about length and width, and you can use whatever letters you want, but I mean, try to make them make sense. Here I'm going to use L for length, and I'll use W for width. Now the other thing that's mentioned in here is something about the area of the pool, and commonly we use capital A to represent area. So step one is just identifying variables. Step two, let's see if we can then take some of these sentences, especially the ones that are complete sentences that have some sort of verb like is or are, or any of those kind of definitive verbs that say that we can probably use an equal sign. Turn those into equations. Here I've got a sentence that says a rectangular pool is twice as long as it is wide. And that particular sentence is actually an equation. A pool is twice as long as it is wide. The length is going to be twice what the width is. Thus length is double width. So that's just doubling is multiplying by 2. Length is equal to 2 times width. Now in the next sentence down here, we see that the area is 50, and that's a really basic equation. Area is 50. Now in some cases, it's not just a matter of turning these into equations. Sometimes you also need to draw a picture. In this case, you might want to draw a picture of a rectangle, and you may want to label the sides of it. And I'm not drawing this at all to scale, but definitely the length should be longer than the width. It should be about twice the length. Now, after you've translated some of these sentences into an equation, that typically means you don't have to go back and continue to read it. At this point in time, you're going to try to see if you can find some sort of relationship that you may already know or that you might be able to look up. Find some sort of relationship that takes L, W, and A and put them all together. So in this case, the model that we would be using to relate area and length and width is that area is equal to length times width in the case of a rectangle. And to maybe be a little less confusing, let's just use, instead of a times, let's put a little dot. So area is equal to length times W that way. Now we're about to get into the solving step of this, which is kind of the final part of the process, but I actually need to take all of the relevant information and see if I can combine that together. So taking that equation and also taking some of the things I already know about length and area, I'm going to plug those in. Let's substitute A equals 50, and let's substitute L equals 2W. And now you've got an equation that if you simplify it, you can go ahead and you can solve it. In this case, I have a quadratic. And to solve that, I can either decide to put everything on one side, or if I'm very lucky in this scenario, I might just be able to use some division and root both sides. Let's be a little bit more precise here. Typically with quadratic equations, you want to have 0 on one side. So let's do that. And then we can see that we can divide by 2 on both sides of the equation, leaving us with w squared minus 25, a difference of squares. And recognizing that this is a difference of squares, we have 0 equal w plus 5 and w minus 5. And that gives us two solutions, w equals negative 5 or w equals positive 5. And remembering, w means width, so this is going to end up being real measurements, and we can't have a width of a negative 5. And going back to the problem, area was in square feet, so this would then also be measured in feet. So our width is 5 feet, and that means we only have one solution. But are we actually done? First of all, we do need to make sure this solution makes sense. 5 feet does seem practical, but in the question, we are asked for the dimensions. And that's not just one dimension, we need width and length. You may have to go back to one of your previous relationships. At some point in time, we had that sentence where the length was twice the width. And that was from this equation back up here in step 2. And now that you know that w is 5, we can take that equation and figure out what length is. Length is equal to twice the width, and that means that length is equal to 10 feet. And the dimensions for our final answer would be 5 feet by 10 feet. And you can even go ahead and plug that back into our second equation from step 2. Area equals 50? It sure does, because 5 times 10 is 50. Now, there are more than one kind of problem that we may involve using rectangles. We may also be interested in the perimeter. For instance, maybe instead of a pool, we have a garden and we need to put a fence around it. Or we could be taking a look at other shapes, maybe not rectangles. Maybe, for instance, we want to take a look at triangles. And here's a very common type of problem involving triangles. Okay, here I've got just a basic triangle, and let's label the sides A, B, and C. Now, what I can do with that triangle is I'm going to make a copy of it, but I'm going to increase the size of it. But I'm going to do that proportionally. So you can see it really looks like the same triangle. It's just scaled to be larger. And you can see that the angles are all exactly the same. So it really is more or less the same triangle. However, all of the sides are now quite a bit different length. So we can now take the big triangle here and let's label the sides with capital letters. Okay, so I've got capital A, and that corresponds to just the lowercase a being scaled up to be a larger value. And I've got capital B, which corresponds to the little b side, but it's also being scaled. And of course, capital C corresponds to little c. Now, by a property here about just everything being proportional, we can actually create some ratios that correspond to ratios of the small side simply being the same ratios of the big triangle. One of these ratios could be A over B for the small triangle. Proportionally, capital A over capital B is also the same ratio. Everything remains in proportion, just scaled larger. And then, of course, if you wanted to flip that, we could also have B over A equals capital B over capital A. And think about all the ratios you can form, not just A over B or B over A. We could do A over C and C over A. Or we can do B over C and C over B. Now, the property of similar triangles can also show up in some word problems. And let's take a look at examples. Okay, well, we've got quite a long problem to read through here. But, of course, this is going to end up being a geometric problem, and we might be able to draw a picture so that we don't have to continue to read it constantly. We've got a flashlight on the ground, and it's shining a light onto a wall that is 30 meters away. So we might want to start off by drawing the ground and the wall, and placing the flashlight on the ground. A mailbox is 1.2 meters tall, and it's in the path of the light and casts a shadow on the wall. So you may want to place that mailbox at that location on the ground, partway into the diagram. If the mailbox is 20 meters from the flashlight, how tall is the shadow? Okay, that gives us some more distances, but we're not going to be drawing anything else additional there. We can just imagine having a box placed between the flashlight and the wall. So let's see what that might look like. Now it's up to you whether you want the wall on the right or on the left. I'm going to put mine on the right, and I'm going to place a flashlight here and let it shine out and make sure I've labeled the distance. It's 30 meters away from the wall. And of course I can highlight that and say I've got that information covered. I don't need to look at it again. A mailbox is 1.2 meters tall, and it's in the path of the light, and it's 20 meters from the flashlight. So why don't we put that mailbox here somewhere? And then let's label that distance as being 20 meters. Now that I've got that piece of information, I can highlight it, and I can also label the height of the mailbox as being 1.2 meters. And I can highlight that and make sure I've got that piece of information. And it doesn't seem to appear that I've got any other numerical values that I need to place on here, but what is it that I'm looking at? Again, this is basically step one. What are the variables here? Most of these are lengths, and I can put those down on my image. But there's one other question, and that is, how high is the shadow? Now that would be something I haven't labeled yet, and the shadow is going to be cast from this spotlight across the top of the mailbox and onto the wall. And so with my ruler here, I can now label this shadowy area here and figure out the height of that. Unfortunately, I don't know that value, so we better make sure that we give that some sort of symbol. I don't know, makes a lot of sense for height to be labeled as h, for instance. And in fact, if you wanted to, you could actually give all of these symbols. Maybe you want to call the distance from the flashlight to the wall a distance d. And of course, distance from the flashlight to the mailbox, well, that can't be d as well. Maybe we'll call that x, since it's horizontal. And what does that leave us for height of the mailbox? I can't use h, I might as well use another variable. Why don't I call that y? Now, it may not be necessary to label each of those with a symbol, provided that you've at least put the numerical values on there. But just if we want to, we can now start to sort of form a relationship between x, y, d, and h using similar triangles. And if we take a look at the small triangle, we can use a ratio of y over x or x over y. Why don't we use y over x? And that would be the same ratio of the proportional triangle, the big triangle here that goes from the flashlight all the way to the wall and has h and d. And so there we go. We have the similar triangles sort of relationship here. And we know quite a few of these values, so we can plug those in, and then we can try to solve the equation for h. Plugging in x and y, we have 1.2 over 20. Plugging in the value for d, we have 30. And as it turns out, this is a linear equation, but we just have to do a little bit of rearranging and multiply both sides by 30. And so we have 30 times 1.2 divided by 20. And maybe you need a calculator, or maybe you can simplify. 30 over 20 is 3 halves, and 3 halves of 1.2. What does that get you? And you can verify this. That height would be 1.8 meters. Now, before you call it done, again, just make sure you've actually answered the question. How tall is its shadow? Well, okay, we've got the answer, 1.8 meters. Does it make sense? Yeah, I suppose it does. The shadow is going to be taller than the mailbox because it's casting a shadow from a flashlight that is lower than the height of the mailbox. So I think we've got it. There's our height. All right, well, we'll take a look at some other kinds of word problems that don't just involve drawing a shape like a rectangle and a triangle and looking for some geometric problems. But we'll save that for another video. Thanks for watching, and I'll see you again later.